warm welcome to everyone here in the room, the few people, and also to the many online participants. To the online participants, I hope that you can hear me well and that you can see the slides also. So in the next 30 minutes or so, I'm going to talk about biochar production and use in Sweden from an industrial ecology perspective. And the three main messages I want to share today are as follow. First, biochar can efficiently contribute to climate change mitigation if certain conditions are met in terms of energy systems, biochar stability, and also in terms of biochar use. Second, I'd like to stress that when designing a biochar project, one should seek for direct tangible benefits from the biochar to justify for relative increase in biomass use and also for potential burden shifts. Third, I'd like to mention that to me, life cycle assessment is most informative when it's used in a flexible manner to identify conditions of suitability rather than to provide a definitive answer in a particular case. So in the rest of the presentation, I'll try to clarify these statements. And of course, getting there took me some time. So for those who know me, they probably heard this story many times. But I have a composite background made of a blend of Middle Eastern cultures and European cultures, but I was raised near Paris where I received an education in sciences. From 2014, I started to specialize in energy and environment, and that led me to my first experience with research in 2015 when I worked with the modeling of albedo effect on climate, followed by introduction of new agricultural practices. Just before COP21, I left Paris and moved to Sweden to study more applied environmental sciences, focusing also now on urban flows, waste, water, and energy. And finally, I wrote my degree project in Lebanon, where I studied waste management systems. And that is when Cecilia, who was already my supervisor at the time, introduced me to biochar. And I was told that biochar is a carbon-rich material obtained from the pyrolysis of biomass, and it's very similar in appearance to charcoal. I was also told that it can be derived from various biomass feedstocks, including urban garden waste, and that during its production in different kind of reactors, we can valorize energy or produce energy. And also, biochar is a valuable soil amendment. It can be used in agriculture in tropical climates to improve yields, and also in urban areas it has benefits, for instance, for tree health. Besides, biochar, I was told, is also a way to mitigate climate change by removing carbon dioxide from the atmosphere. And all these keywords that I just mentioned kind of resonated with what I had been doing so far. And that's why in August 2017, I decided to embark on a PhD journey. Now, 4.5 years later, I can tell you a bit more about the biochar's history. And well, the first research on biochar dates back to the late 90s, and it was not yet called biochar, but rather dark earth soil or charcoal amendment to soil. The term biochar itself started to gain in popularity only around 2006, 2009. And in the decade that followed, as I was maturing in my education, so did the biochar research and practice. And I'll say a few words on the research side. Biochar field experiments were set up on nearly all continents, leading to numerous scientific publications and also to a series of reviews on biochar production techniques, but also biochar properties and their effects on agriculture. On the practice side, I'll limit myself to Sweden and mention that the first uses of biochar date back to approximately 2013, when it was used in Stockholm area to plant trees in a new technique that is now famous. And that the first commercial plants, pyrolysis reactors that were installed or commissioned in Sweden date back from approximately 2015, 2017. And today there are, by then at least, there were a dozen of biochar projects in planning in Sweden and many more abroad. So overall, when I started, biochar was presented as an emergent technique available across income levels at the crossroad of bioenergy, biomaterials, and agriculture, and also seen as a potential solution for many global challenges, and in particular, climate change. So let's take a second now to frame a bit the challenge and give an order of magnitude. As you all know, the challenge of the 21st century is to manage to live within the physical boundaries of the planet while also living above a certain social minima. And that's not just for you and me here, but for everyone else as well on the planet. And one important physical boundary we have is the climate change. With limited resources, we have to be able to reduce our emissions of greenhouse gases. And well, today, globally, our emissions are roughly at 50 gigatons of CO2 equivalents per year. And they need to reach zero sometime in the second half of the century. But we know that there are also some emissions that are difficult to reduce, for instance, in agriculture. And the climate scientists then tell us that we will also need to remove excess carbon dioxide from the atmosphere. But how much we need to remove and how much we can remove is slightly uncertain. How much we need to remove depends on the emission pathway that humanity will take, and how much we can remove is actually limited by the resources we have available. Nevertheless, an order of magnitude we commonly use is roughly around 10 gigatons of CO2 removed per year. And that's already a massive amount. So if I summarize here, the challenge is to be able to mitigate about more than 40 gigatons using behavior change, efficiency gains, and also low carbon technologies. And in addition, we may need approximately 10 gigatons of removals. So here I want to make clear that removal technologies are not a magic bullet, they're rather the icing on the cake, or as we say in French, la cerise sur le gâteau. So, removal technologies are to be deployed, but also when and where they make sense as a complement to a coherent mitigation strategy. And the question here is, when and where does biochar makes most sense? So although biochar is not yet included in global climate scenarios, it's recognized as a serious removal option. But it's not only that. We must not forget that biochar is also energy co-production during the pyrolysis, and also that the material, biochar itself, has a value, both of which can contribute to further climate change mitigation beside the sequestration part. And they also have other environmental effects that we need to analyze. Second, I'd like to mention that biochar systems are extremely diverse, that they are available on all continents. They vary in terms of size, in types of biomass and reactor, and also in terms of application for the biochar. And these multiple configurations we have there potentially lead to very different environmental performances. So at the same time as pilot projects are initiated, there is a need for assessing them, both to be able to learn from the pioneers who are trying out things with biochar, and also to be able to influence future projects and maybe policies even. So therefore, the aim of my thesis were to evaluate the energy, climate, and environmental impacts of biochar production and use. And part of the objectives in the thesis were about understanding the structure of the life cycle impact from biochar projects, and the other set of objectives were related more into conceptualizing biochar effects, whether it is on energy systems or arising from the biochar use. But part of the aim was also to support ongoing and future projects in Sweden, and therefore we included various case studies. The first case in Stockholm studied large-scale biochar production connected to an energy grid, the Stockholm district heating network and power grid, and an explorative use of biochar on dairy farm was considered. The second case focused on small-scale production of biochar integrated to the local energy demand of a farm. And the last two case studies in Helsingborg and Uppsala focus now on urban uses of biochar. So biochar was produced or assumed to be produced in medium-scale reactors from different kinds of biomass, And the applications we considered were remediation of contaminated soils, urban greenings, concrete mixes, and also water filters. But for each case we have performed, we did environmental assessments. But we also wanted to answer specific questions that were of interest for the different stakeholders involved. So in Stockholm, we wanted to look at the effects of a large pyrolysis plant on the local energy system. At the Lindeborg farm, which had just received its new pyrolysis reactor and was facing some operational issues, we wanted to understand these. And in Helsingborg, the focus was, of course, on toxicity of the remediated soil that you see here on the picture. And for the Uppsala municipality, a key question was to know how much biochar can actually be used in a neighborhood, in a typical neighborhood. So, in other words, the case studies we have performed have influenced our research, but also the methods that we have used. So, the main methods was life cycle assessment, or LCA. And I always use LCA in a comparative manner. So I'm comparing different alternatives that deliver a similar function in a given context. In practice, this translates to, when we want to describe one alternative, into first defining system boundaries, life cycle stages and processes. Then we have to quantify the physical relationships between these processes and also their direct environmental emissions. And finally, with that, we can calculate impact scores and contributions, which must then be interpreted. And in combination with life cycle assessment, I use other modeling tools and technique, and that was mainly to be able to either quantify the physical relationships between the processes or to be able to push further the interpretation of the LCA. Among these methods, complementary methods, one of them relates to energy modeling. And I have mainly used enthalpy balances to be able to describe pyrolysis processes and also unit commitment models to simulate the operation of pyrolysis plants in different contexts. And that was mainly done in paper 1 and 2. Then we also used material and substance flow analysis, both in their static and dynamic versions, mainly in papers 3 and 4, for the toxicity assessments and for biochar demand estimates. So, moving on to the results now. The first result I want to present is actually related to the experience that we have gained in making assessments of biochar systems, and it takes the form of a flowchart. It starts with biomass production. That involves cultivation of land, application of fertilizer, use of machinery for harvesting, and also direct soil emissions. If we consider garden waste, for instance, it can also represent the preparation of the feedstock and the collection of the waste. The next step is the thermochemical conversion, and that can include the drying of the biomass, its size reduction, and also then its pyrolysis. From there, we get two different streams. The pyrolysis gases and tars, which can usually be combusted directly on site to produce energy. And the biochar, which is used in combination with other materials to manufacture a biochar product. And this product has, of course, a use phase and an end of life. And there are many different products based with biochar. So here, we see that biochar systems are multifunctional. The biochar product has a function here. For instance, so the cleaning some water or planting a tree. From the combustion of gases and tars, we get energy, which is another function. And since we're dealing with biomass, we also have either a reference land use or an alternative biomass fate, which can also deliver some services. So for all these functions, we can and should define what we call a reference system, here shown in gray. So related to this reference system, a second piece of result I would like to mention is that biochar effects are always relative. To clarify, so in the literature and also in the public discourse, biochar is presented as a removal technology that comes with many positive side effects. And I mentioned some earlier. And we tried to classify these effects also in a life cycle perspective, and I'll take some examples. So we commonly hear that biochar in a landscaping context, so in urban areas, can reduce the use of peat. But that, of course, is relative because it assumes the current consumption of peat products in our economy. So there is a reference activity where we would use more peat than with a biochar product instead. And here's the type of effect we defined in LCA is what we have called a change in technosphere input, because it's related to a product that you're consuming that you're changing the amount of. A second example would be, for instance, in agriculture, if we consider reduction of nitrous oxide emissions from soils following the application of fertilizer. That can be an effect measured in the field when we apply biochar to specific soils. But that, of course, assumes a reference situations where biochar is not used and emissions are higher. And here, it's not a change in technosphere inputs that we're modeling, but it's more change in biosphere exchanges, so a biological process that is affected. And finally, a third example would be, for instance, when we say in urban areas that biochar can improve tree health and thereby reduce mortality of trees. Here, we describe it as this time a change in technosphere output. So the product, you get more product for a given amount of resources. But I would also even say that biochar carbon sequestration is also a relative effect because it depends on the assumptions you make on the alternative fate of the biomass. So if we want to summarize this here, we can also make a parallel with experimental sciences. If you conduct an experiment in a field, you would like to set up a control, or sometimes you have several controls to be able to measure an effect. And we have the same notion in LCA, which is basically that we have to define reference situations. Right. So if environmental efficiency is relative, it's also the case for the climate impact of using biomass in a biochar system. Here, I'm showing a selection of climate impacts that we have calculated in the different case studies. But how to read this figure? Well, every row in this figure represents different biochar system. For instance, the first row here is a pyrolysis plant in the Stockholm context that is compared to a conventional heat and power plant, CHP. And I'm calculating the climate impact expressed in tons of CO2 equivalent per ton of biomass in two different energy contexts, in the Swedish average energy context and also in a fossil energy system. Then on the graph, I'm showing different contributions, which are the three colors. One of them relates to carbon sequestration in the biochar. In blue, we have everything related to energy substitutions. And then in green, we have the material value of biochar, all the other effects related to biochar. So these were the contributions. But on this figure, I also show net scores, and I actually show two of them. The first one is the cross here. It's a net score of the system that includes carbon sequestration. And here, the assumed stability of the biochar is of around 80%. But I also show another one, the dots, which correspond to the same system, but without accounting for carbon sequestration. And there are several reasons why we like to do this. And one of them is that biochar stability is uncertain, and that in the worst case, it could be zero. But there are also other more subjective reasons why we also want to look at results without accounting for carbon sequestration. So now, three messages from this figure. First, if we look at the Swedish average energy system, we see that all biochar scenarios are able to outperform the reference. That means that actually all the crosses are below zero. And if we exclude carbon sequestration and we now look at the dots, you will notice that some of them are not outperforming the reference. And that is the case here for these three scenarios where we don't have any explicit biochar use. And it's also the case for this one here, which is a concrete where actually the biochar recipe for concrete uses more cement than the reference. So there we have actually increased emission from cement use. A second message here, if we look at the numbers, is that carbon sequestration in biochar ranges between 500 and 900 kilograms of CO2 equivalent per ton of biomass used, and that all the additional effects of biochar, if they exist, so the green bars, were in the range of 10 to 100% of the biochar carbon sequestration. So in other words, additional effects from biochar use can up to double the benefits from carbon sequestration, for some applications at least. Finally, if we now look at the fossil energy system, one thing you should be able to notice is that the blue color is much more predominant. The energy substitution term is enlarged. And that we also have to make a distinction between all the scenarios that are above this line and the one that are below. And that is a difference between our assumption on the alternative fate of the biomass. So when we are looking at above the line, all these scenarios assume that biomass would otherwise be used for energy production through combustion, for instance. And in that case, we see that biochar systems suffer from what we call an energy penalty. And in very few cases only, these systems, the biochar can win over the reference. In turn, when we do not assume that biomass would be used for energy, then the pyrolysis energy appears here as a benefit because it's going to substitute fossil fuels. So here it highlights that the way we make our comparisons in LCA can also influence our interpretation of the results. Okay, now leaving the climate impact on the side and looking at other impact categories. We have assessed resource use and other toxicity impacts using the ILCD metrics. And here the picture is overall less clear than for climate change impacts. What we can say, nevertheless, is that there are some burden shifts, and that in some cases, it basically depends very much on the context we are in. And I'll give one example. For instance, in landscaping, if we're considering moving from peat to biochar for landscaping products, then we saw that land use impacts could be both increased or decreased depending on the type of biochar we are considering. Second, another interesting aspect is here related to the biochar supply chains. So biochar can be produced in many different ways, and we realize that differences in impacts between this way of producing biochar could be larger for other impact categories than for climate change. And one example here is when you look at reactors to produce biochar that are driven by electricity versus others that are driven by syngas. In the Swedish context, these electricity-driven reactors had much higher impacts in terms of ionizing radiation and fossil resource depletion because of the high share of nuclear power in Sweden. And finally, a last point I'd like to mention here is a bit of an issue when we consider toxicity impacts, and that we are comparing data taken in the foreground LCA for data collected from the actual project we're studying, and background inventory data from a database like EcoInvent. For instance, stack emissions in a pyrolysis reactors, we had data from the project, and we in the reference, so in the background database, we use combustion data from EcoInvent, where the scope of emission inventories were very different. That's something to bear in mind when we look at toxicity impact categories. And a last piece of results I'd like to present is related now to insights that we got from the case studies. So in the Stockholm case, we have used a unit commitment model representing the district heating network. And this model was provided by Stockholm Exergy, one of the operators of the district heating grid here. And this model allowed us to quantify net changes in biomass and fuel consumption at the city level. One interesting aspect was that the construction of a new pyrolysis reactors and connecting it to the city would actually displace the use of older biomass boilers and also to some extent large-scale heat pumps. In the Lindeborg case, we also used a unit commitment model, but this time at a daily time scale to understand operational constraints at the farm. And basically, heat demand on a farm can look like on this curve. It's low in the summer, and it's much higher in the winter. So a pyrolysis plant can deliver heat to that farm, but only between its minimum and maximum capacity. So here, in theory, we could expect the pyrolysis plant to operate between November up to April. However, in reality, the heat demand is not that smooth, and it will look more like this. And because of that, this implied that pyrolysis use or the use of the pyrolysis reactor could be shorter than expected, and also facing some shutdowns during the wintertime. And also need then to be complemented by other heat sources like electrical heaters or heat pumps. So this information was taken into account in our LCA, but it also allowed us to quantify biochar production at the farm depending on the climate. And so we estimated that for the farm that we studied here, biochar production could vary between 7 and 12 tons per year. And that represents about less than half than the capacity, the maximum capacity that the reactor has if it would be operating continuously all year long. But this said, we must not forget that a pyrolysis reactor operates probably for 25 years, or at least has a lifetime of 25 years. And during that time, heating demand may change. Due, for instance, to climate change, it could be reduced. And if the farm decides to build more buildings or even to dry some grain in the summer months, then heat demand could also increase. So the key message here is that dimensioning is a key factor, especially when we are talking about small-scale and heat-constrained system. That is a very important step as it affects the time and the economy, but also the environmental performance of the project. Finally, in the Uppsala case, we have also estimated our biochar consumption. And we estimated that there would be about 2,000 cubic meters of biochar needed to be able to build this given neighborhood south of Uppsala. We were also able to calculate climate change mitigation potential at the level of the district. And one interesting aspect here was to show that depending on what type of biochar, this potential could vary, and that a key parameter here was also the bulk density of the biochar. So I'm now done with presenting the results, and I just have a handful of slides left. And I'd like to start with some reflections on my work. A first reflection I'd like to make is related to the global climate context that I presented earlier. And I came to realize that the goal of biochar and other removal technology is not primarily to remove carbon dioxide from the atmosphere, but rather to mitigate climate change. And the difference may be subtle, but I think that it's an important one, especially when we are considering multifunctional and bio-based systems. And biochar is one of them. Second, an unanswered question in my work is the availability of biomass to produce biochar. We have always assumed that biomass was available, mainly because we wanted to focus on what was new to us, the pyrolysis operation, and also biochar applications. But now that we know more about biochar systems, about their efficiencies and the different applications, I believe that it's time to include biochar into larger models and probably also work with more integrated and optimization techniques, while still, of course, keeping in mind the life cycle perspective. Indeed, I believe that the life cycle perspective is useful in sustainability science. It's useful to avoid what we call shifting of burdens between impact categories, but also between sectors and also generations. However, the more I work with biomass, the biosphere, or what we call the bioeconomy in general, the more I realize that classic LCA, which is static without an explicit time dimension, is facing some obstacles. In particular, if we try to model biogenic carbon flows over time and space, and also if we want to make scenarios, model scenarios under resource constraints. For that, we need different, I guess, models. Here, I would say that a common objection that is often raised and that I've encountered several times is that is this opposition between complex models and simple models. But well, we all know that models are wrong, but they need to be useful. And I think that a way forward in this dilemma is that if we cannot avoid the complexity, then we should be able to make models that are at least simpler to use. And this implies, to me at least, that we need to work for better modeling practices and also better research tools. And there, I believe that the open source research communities is very useful. And I have myself benefited from various codes that have been published by others online, avoiding me to start basically everything from scratch or reinvent the wheel. So finally, I would also like to mention that during my research work, I've had the chance to be in interaction with many different stakeholders. And I must say that the biochar world is a very dynamic sector. Over the past 4 years, I have seen an increasing number of persons working with biochar in Sweden and also abroad. And that sometimes we had the feeling as researchers that these private actors were moving faster than us with their own agendas in mind. But that we also had sometimes a mutual influence on each other, on the way of working and data choices and similar things. As a research team, we were also glad to be able to contribute with our knowledge to some public or political processes. And one example here is, for instance, the recent inquiry in Sweden on negative emission technologies. In essence, all of this were somehow very enriching experiences in my research journey. Having said all this, I think it's now time to look back at the main messages that I showed earlier. I hope that they are clearer and that we can even be now more specific about them. So when I mention decarbonized energy system, I mention here actually everything that is well below natural gas. When I talk about high biochar stability, I think the good value is around 80%. And when I say a purposeful use of biochar for climate, then we can also think of mitigating other greenhouse gas emissions in agriculture or replacing high impact materials. Then a recommendation that I always give to biochar stakeholders is that ideally, in the best of the cases, their biochar production and use should not be mainly driven by carbon removal, but by something else that they find useful for their activity. And finally, I think that for me, a further area of work will be to work more with algebraic, modular, or integrated LCA modeling. With this said, I'd also like to thank all the persons who contributed to this work, and that includes some funders, my supervisors, and also co-authors Asterios and Anya, and all the other ones that revolved around my work, mentioning also the students that worked with me in the past few years. Thank you, everyone. And